Hello everyone. Today, I am excited to share with you our latest research on Weakly-Supervised object detection, titled Random Prompt Assisted Weakly-Supervised 3D Object Detection, or Prompt3D. As we know, object detection in 3D scenes is a challenging task, especially when we have limited labeled data. Traditional methods rely heavily on fully supervised learning, which demands extensive and detailed annotations. However, obtaining such annotations is both time-consuming and expensive. Besides, synthetic data may perform poorly on real scenes due to the domain gap. To address the challenges, we have developed a novel approach that leverages weak supervision while maintaining high detection accuracy. This figure shows the overall process of this method. This method uses low-cost position-level annotations for supervision, uses synthetic scenes constructed from 3D shapes generated by random prompts to enhance weakly supervised annotations, and proposes a prototype proposal feature alignment module to achieve knowledge transfer from synthetic scenes to real scenes. Specifically, our method, Prompt3D, introduces two key modules, the Synthetic Scene Generation (SSG) module and the Prototypical Feature Alignment (PPFA) module. Let me start with the SSG module. The Synthetic Scene Generation module creates synthetic scenes using 3D shapes under weak supervision. It constructs synthetic scenes that approximate real-world layouts through two steps: prompt-to-mesh translation and 3D shape assembly. In the first step, prompt-to-mesh translation, we create synthesized scenes by using 3D shapes generated by SHAPI through random textual prompts. These prompts help us create a diverse set of shapes, enriching the variety of our synthetic scenes. By doing this, we introduce a strong supervisory signal even in the absence of detailed annotations. The generated synthetic scenes, though not real, provide substantial context and object diversity, which significantly aids the learning process. Moving on to the second step, 3D shape assembly, we segment real scenes using a normal-based graph cut method to identify geometric plane components, and then use a different method from previous studies to associate each weak annotation with its surrounding possible related geometric components, and use the shape information of these geometric components to approximate the shape of our annotated objects. We can then generate an initial virtual scene by selecting the most fitting 3D shapes from the 3D shape library generated in the first step to replace objects in the real-world layout. Next, we adjust the virtual scene layout by applying gravity and collision constraints, ensuring realistic positioning and interactions between objects. Finally, we generate precise ground truth bounding boxes for each instance, facilitating accurate and comprehensive annotation of synthetic scenes. However, there is an inherent domain gap between these synthetic scenes and real-world scenes. To bridge this gap, we developed the PPFA module. This module minimizes the L1 distance between each prototype of the same category in synthetic and real scenes, thereby aligning the feature distribution between domains. By aligning these features, we effectively transfer the knowledge learned from the synthetic scenes to real-world data. This alignment is crucial as it ensures that the model learns relevant and transferable features, thus improving its performance in real-world scenarios. In addition, to avoid introducing invalid proposal features, this method introduces a foreground proposal mask to select features that are more likely to belong to the foreground proposal to participate in the alignment. As the training batches accumulate, the calculation of proposal features becomes more and more computationally intensive. To alleviate these problems, this method adopts an online estimation algorithm to estimate the prototype. This is the overall framework of the above two stages, with the SSG module on the left and the PPFA module on the right. We evaluated our method on the widely used indoor dataset ScanNet. Our experiments demonstrate the effectiveness of Prompt3D in narrowing the performance gap between weakly supervised and fully supervised object detection. Specifically, when using VoteNet as the detector, the performance disparity with fully supervised settings was reduced to just 7.7% MAP at 0.25. Moreover, compared to the previous state-of-the-art method, our approach achieved nearly a 2% improvement in MAP at 0.25. When employing group-free 3D as the detector, the results were even more impressive. The performance gap with fully supervised settings was further reduced to only 3% MAP at 0.25, reaching a performance of 51.2%. Now let's dive into the visualization of our method. The image on the right showcases a synthetic scene created by our approach. Thanks to the diverse shapes generated by the hint text, these synthetic scenes appear more realistic. Moving on to the detection results visualization, our method consistently achieves accurate detections in scenarios where WSB and BR methods falter in locating objects correctly. We use ablation studies to verify the effectiveness of the two proposed modules. The results show that the proposed SSG and PPFA modules have effectively promoted the performance improvement of weakly supervised networks. In conclusion, Prompt3D offers a promising solution to the challenges of weakly supervised 3D object detection. Our synthetic scene generation technique provides a cost-effective and scalable solution to the problem of limited labeled data. By utilizing random prompts to generate diverse 3D shapes, we can continuously expand our synthetic dataset, thereby improving the training process without incurring significant annotation costs. By leveraging synthetic scenes and aligning prototypical features, we can significantly enhance detection performance while reducing the reliance on extensive labeled data. Our experimental results on ScanNet validate the effectiveness of our approach, highlighting its potential for broader applications in various 3D object detection tasks. Thank you for your attention. For more information, please visit our project webpage. I look forward to your questions and feedback.